Afternoon session. Professor Melnikov is returning today for continued talks on unsupervised learning and mixture models and model-based clustering. We have two 50-minute sessions and a 10-minute break. Yep. Okay.
Hi everyone. Yeah. So this is the slide where we stopped last time, and right now we will talk about some challenges in finite mixture modeling. And I will try probably to speed it up a little bit, because I think we covered last time, like as I can see, this is slide 24. So at least something probably we will need to skip, but okay. So the first challenge is, like, there are some challenges related to regularity conditions, and the first one is that likelihood function oftentimes is unbounded, and this is a serious problem, but it's not always the case. Actually, it depends on the particular mixture model. So, for example, in famous Gaussian mixture models, the likelihood is unbounded if we have unconstrained covariance matrices. So basically, if covariance matrices are allowed to be anything, there is absolutely nothing that prevents a covariance matrix to be constructed basically on one observation, and in this case we have an issue. Our likelihood goes to infinity. This is like a serious concern. There are some remedies in literature. One of them is to use mixtures that are free of this concern. Like one of them, for example, is a Gaussian mixture with equal covariance matrices. If you assume that covariance matrices are equal, it's like there are some papers that show that the likelihood is unbounded, everything is in place. Another possibility is to use a restricted parameter space. So what usually people do, they set some ratio on the values of eigenvalues so that there are no covariance matrices that are too stretched, basically. There is an approach on penalized likelihood function, but I think by far the most popular approach is based on best local maximizer. This depends on relies on the result provided by Kiefer in 1978, and it shows that even if we have a likelihood that is unbounded, if we are able to find the best local maximizer, it will have essentially the same properties as the properties of the global maximizer if the global maximizer exists. So basically what people do in mixture modeling in practice, even if you have something like a mixture of Gaussian mixtures, a mixture of Gaussian components, and you know that the likelihood is unbounded, you still feed it with different initial starting values, and you try to find the best local maximizer, basically. And then you essentially hope that it will have nice properties. In general, of course, you never know for sure whether you found the best local maximizer or not. And this is why when we talk about this initialization is so crucial. Another challenge is that actually finite mixture models have issues with identifiability. So what is identifiability? Essentially, we don't want to have different sets of parameters to produce exactly the same distributions. But you can very easily see, like in this example, that it is enough to switch theta 1 and theta 2 in these two components, right? And we will get exactly the same model. Some literature, like for example, I can actually recommend a very good book written by McLaughlin. It's called Finite Mixture Models. So what he recommends there, basically some using, he refers to Aitken and Rubin, and to introduce some additional restrictions on the parameters. So for example, mixing proportions should go in ascending order, or like the first coordinate of the mean vector, or maybe both, or similar things, so that at least maybe, if not resolved entirely this non-identifiability issue, but at least to relax these concerns. All right. So now we will talk a little bit about the initialization strategies. And as I already mentioned, likelihood, especially for complicated models, has multiple local maxima. Yes?
So, why is it an issue if two different parameters result in the same density? Like if it results in like clustering the data well, like why do you need to recover the parameters from that?
So it's related to likelihood inference, and one possibility, like one thing about non-identifiability is that if basically you have like you can think about it in the following way. If you have different sets of parameters producing exactly the same PDF, right? It basically means that you're using some extra parameters that you can get rid of, right? So, and strictly speaking, if the goal is only clustering, it may be not an issue at all. It's just, you see, your model is not going to be so interpretable because there is an infinite set of parameters for which you will obtain the same result. Pretty much. All right. So, unfortunately, I think too little attention is paid to initialization issue in practice. And well, just because I work in mixture modeling, I review papers in mixture modeling all the time. And I can tell you that the approach that people most frequently use is either employ random partitions, just literally assign observations to clusters completely at random, or use something like k-means. So run k-means, get the initial partitioning, and then run your EM algorithm from there. There are problems with these strategies unless your model is very simple. If your model is some very simple, like maybe you have 2 components or 3 components, oftentimes, essentially, it doesn't matter where you start. You just maybe rerun the EM algorithm a couple of times and you get a good result. But unfortunately, there are situations, for example, when you have many clusters or you have elongation in clusters and like more complicated structures where such approach it cannot be recommended at all. If you think about random partitioning, we literally assign observations completely at random. So imagine that we have some structure, maybe, I don't know, some 5 components, maybe like this, right? And if you assign observations at random, so literally you started with some covariance matrices like this. It cannot be a good starting point, right? So another thing is that even k-means is not necessarily a good approach because as we discussed last time, k-means introduces also constraints, right? It very much favors spherical clusters of the same size, right? So, and if you have elongation in clusters, you might start in such a wrong place in the parameter space that you will never actually reach, like you will never find. You can reduce your chances of finding the best local maximizers tremendously just by starting your EM algorithm with not appropriate initialization strategy, right? So I think EM algorithm is a very promising algorithm. So it was proposed by Bernanke. Bernanke is in the University of Lille right now, and this is a very interesting approach. The idea is the following. So you start with random seeds. I will try to briefly summarize what it does. So imagine that you are looking, for example, for k clusters. So you choose k data points from your data set, and you assume that these are going to be your cluster centers. Then you assign observations based on the proximity to a cluster center. So it starts pretty much like k-means, but this is like k-means with just one iteration. And then you stop, and you get some very like pretty much random partition, but it has more, like it's more meaningful than this one. But you can have clusters of different size. You do not necessarily have spherical clusters, so you have more variability in the structures of clusters you obtain. After that, you run what is called the short EM. So this is the EM algorithm that you run maybe for something like 5 iterations or until some Lex convergence criterion is met. And you repeat this process many times. Like, how many depends on the complexity of your situation, but let's say 100 times. And you find the most promising solution. Promising in the sense of the likelihood, how high is the likelihood obtained after, let's say, 5 iterations. And you pick that solution, and then you run the lone EM until the final convergence. And this is much more, like, this is a much more promising approach for initialization than something based on K-means. But again, like, even in mixture modeling literature, I think 90% of papers use either random partitioning or K-means initialization, despite the fact that it's So basically, if you do a good initialization, most of the results in those papers you can beat, actually. So, there was a modification proposed in 2009. It's essentially pretty much the same as the EM-EM, but I mentioned it because it was proposed by my advisor. So, it's what it does, it calculates likelihood immediately. So instead of running short EM for several iterations, you literally get this random partitioning right away, and you estimate the likelihood, you calculate the likelihood based on that set of parameter values right away. So what does it give us? We don't need to run many short EMs for several iterations, so it can be actually good in the case when we have many clusters and we are trying to, and they're well separated. But if clusters are not very well separated, you want to go a little bit deeper in the EM algorithm. So in this case, actually, it is better to use something like EM-EM with, I don't know, 5 iterations or something like this for the short EM. There are some other attempts. EM-AEM. This is basically very similar idea to the EM-EM algorithm. The difference is that if you think about what EM-EM does, we choose only one winner, right? Only the best option out of multiple short EM algorithms. And this algorithm does something like averaging of those solutions, because many times we will pick correct clusters after running the EM algorithm. We will pick the correct cluster. Maybe 2 of them are going to be incorrectly detected, and the rest of them are going to be well detected quite well. So we can do something like related to averaging over the solutions obtained from short EM algorithms. And sigma EM, it's another algorithm. I actually have something a little later, I think. Okay, this is an illustration for MDM that I wanted to show you and why this initialization actually is an issue. So here I have just 10 clusters, 10 Gaussian components, and I initialize it 6 times here. And you can see that until time number 6, I couldn't reach basically the correct solution. In this case, you can see that one cluster got split, right? And this cluster there are 2 clusters here and they got merged. Here we will talk about this kind of solutions, the sort of spurious solutions, and here as well. Here again we combine several clusters. So this problem, even though like 10 doesn't look like it's an extremely high number, but it's actually very difficult to initialize correctly. And RandEM is not the worst method. If you try K-means on something like this, most likely you will not find the solution. I will probably just very briefly talk about the sigma-EM idea. The idea is the following. If you think about your data points, and in the places where you have clusters, the density of points is going to be higher, right? So around the core of the cluster, you're going to have a high density of points. So what if we construct we take a hypersphere around the cluster center, where we have very high, in those areas where we have a high density of data points. And then based on this hypersphere, we will actually take those points covered by this hypersphere and include it inside of it. And we treat it as basically as truncated normal. This is for a method for the Gaussian mixture model. So what if we treat it as the then we can establish a relationship between the variance of the truncated normal and the variance of untruncated normal distribution, right? So it's under the assumption that normality holds here. So after we update, we can estimate the variance of the truncated normal distribution, and we can estimate the variance of untruncated normal distribution. Based on the variance, we can construct, I think I have a picture here, we can construct an ellipsoid that will include more points. More points implies more information. We can estimate our variance better, and it's an iterative method where we basically include more and more points, include more and more information, and until our truncated normal distribution becomes essentially normal distribution. After we identify one cluster like this, we can take all the points out of the data set, find another area with dense points where the points are very close to each other, and repeat this algorithm again and again until basically all clusters are eliminated. There are some technical concerns, of course, issues. If clusters overlap, we might actually proceed and take another cluster included in the covariance. So each cluster has to be also checked for the inclusion of multiple clusters. So it's like a multi-stage procedure. But it actually works quite well if we in the situation where we have many clusters. This is just an example that where is sigma m here. So it detects everything correctly and without big issues. But, and this is the original data set that's simulated. And this is the MEM performance, RAND-EM, k-means initialization, and I think average linkage with hierarchical clustering. One thing I want to mention, there is ARI. So this is adjusted RAND index. This is the index that is very commonly used for comparing partitions. So the upper bound of this index is 1. 1 happens if two partitions match perfectly. And another important value of the adjusted RAND index is 0. This is the value we observe for random assignments. If, for example, we have like two partitions that are simulated at random, expected value is going to be 0. So values around 0 imply that we have no match at all, like on average. So basically, the closer we are to 1, the better. So we can see that sigma m shows pretty good performance, but this is, I think we will proceed to the next topic. So next one is related to merge and mixture components. We already talked about this somewhat. And this is an illustration. If we are in the situation when we have two clusters, right, two components that are quite well separated, we can see these two humps in normal distribution. But now, if I start moving one component toward the other one, right, the separation actually decreases, overlap between these two components starts increasing, and at some point, actually, you can see that we have a component like this, right, that can be used for modeling skewed data, right? But the issue is, and if you think about two Gaussian components that are exactly the same, so eventually, when you overlap completely, right, you're supposed to have, like, you are modeling only one group by using two components. So eventually, at some point, you have to decide that, well, there is only one cluster. So basically, the message here is that several components can be needed to model just one group of data points. But in this case, our effective one-to-one relationship between mixture components and clusters will be broken. So there are two major approaches. Oh, by the way, yes, this is an important conclusion that identifying a good mixture model is not necessarily equivalent to finding the optimal partition, like good partition. And two approaches popular in literature. One is based on what is called model-based clustering, not model, but more based on modes. And based on this approach, people try to identify local modes in your data and assign the zone of influence for each mode and basically make assignments of the other points based on these zones of influence. But there are some issues with these approaches. They didn't become very popular because they are very computationally demanding, and oftentimes they just catch some local modes and produce clusters that have like pretty much meaningless. We have no interpretation, not systematic data patterns, but rather random. And there are some emerging mixture components. This approach is much more popular, and typically they rely on some measure of interaction between components. But this approach can produce multimodal clusters. So sometimes it is fine, sometimes it is not, but it can produce multimodal clusters. Okay, so the first merging approach was proposed by Baudry. It's also a group from France. They proposed it in 2010. And they used the idea based on entropy. So they measured the change in entropy associated with merging components Ck and Ck prime. These Ck and Ck prime, they contain groups of several components already included in there. And if there is a high value of the entropy change associated with merging, so basically high values of course favor merging. And if the assignment, if there is a very big separation, then this change is going to be pretty much zero. So high values of nu favor merging. Excuse me. All right, so this is what they do pretty much. They construct a dendrogram, trying to merge at every step they merge those groups of the components. They merge, and then in the end, of course, they need to decide how many clusters are there. And what the authors proposed, either use ICL, and we talked about ICL last time briefly, right? This is a method that people tend to think that it is better to find the number of clusters rather than the number of components. Or they even actually proposed the two-piece regression, so basically an elbow method where you construct like two-piece regression, right, and you find the point where this change in the regression line happens. Okay, another approach was proposed by Christian Hennig from the University of Bologna. He called it DEMP, directly estimated misclassification probabilities. And the idea is sort of intuitive here. The closer these components are to each other, the higher misclassification probabilities are going to be. Right? So if we somehow can estimate these misclassification probabilities, we can use it as a tool for deciding whether we need to merge components or not. So omega j given k is misclassification probability, and this is basically the way how he proposed to estimate it. One thing I think is not particularly good about this approach, and as about actually previous one, is that if you think about what we're saying, we're merging components. Components are actually distributions, right? But these formulas, everything is based here on a particular data set. So sort of like it would be nice to have a tool that is solely based on the parameters of your distributions, right? Of parameters of your components rather than particular values of your observations. So, and there was a proposal, right? So in 2016, it was like, it's a very similar method to what Hennig proposed. It's just we can actually calculate, in some cases, even get analytical distributions. We can get results for these misclassification probabilities without any attachment to a particular data set, just purely based on components. The idea is the following. This is misclassification probability. This is literally, this is the probability that if we think about how the model-based clustering works, right? We assign observation to a class with the highest posterior probability. So if we compare two components and we work with pairwise misclassification probabilities, we basically compare two clusters, let's say two components, component K and component J. And misclassification probability if tau ik is less than tau ij, when we know that actually our observation came from the K component. So in this case, we observe misclassification. If we have more than two components, but groups components, we can also write it like this. And I think I touched something. So we can give an extension for the groups. And in general form, we can use Monte Carlo simulation just to calculate this misclassification probabilities. This is very, very simple, basically. But in some cases, simulations are not even needed. We will talk about this case a little bit later. So this is the case when we have just one component for the group of components. Okay, so this is to calculate the initial overlaps between pairs of Gaussian components, between all pairs of Gaussian components. And this can be shown that basically this misclassification probability can be calculated as a probability of a linear combination of independent non-central chi-squared random variables with 1 degree of freedom. All right. I'm much faster today, right? All right. So now very little about variable selection. That's another issue. Basically, if we're interested in cluster analysis, very often variables do not carry any information about clustering, right? This is possible. Another thing is that information can be redundant also, right? So some variables can have exactly the same information as other variables that are already included in the model. So it would be good to get rid of them. And this is like a small illustration of what can be a relative variable and what can be an informative variable. So here, as you can see, we have like 3 clusters. But if I drop this variable, I call it irrelevant, and I will not lose anything in terms of detecting the clustering structure, right? It will be as simple as right now. But in this case, both variables are informative. If I drop this variable, I will not be able to separate red and blue clusters. If I drop this variable, I will not be able to separate green and red clusters. So in this case, both variables are important, and we would like to keep both of them. Some examples that it actually can make difference, like some famous data sets available from UCI data repository. Some famous IRIS data set, it has like 3 classes, Setosa, Versicolor, and Virginica. Each class is presumably has 50 flowers in each. And if we fit the Gaussian mixture model, we obtain like 5 misclassifications, because Versicolor and Virginica overlap quite a bit. But if you drop, I don't remember which one, I think number 3, if I remember correctly. If you drop just one variable from IRIS, you can actually reduce the number of misclassifications. It's very easy to check. For wine data set, wine has 13 variables, 178 observations originally. If you drop 10 variables, actually you can very much reduce the number of misclassifications. So actually it's a very good and very helpful technique to reduce the number of variables in cluster analysis, and it can help dramatically. But those methods are like, it's still like lots of work can be done in this direction. I can just show you a little bit of what people do here. One idea was proposed by Adrian Raftery from University of Washington and Dean. So they split the variables into 3 sets. Y1 includes the variables that are already included in the model. Y2 would represent the set of variables that is currently under consideration for potential inclusion in the model. And Y3 is everything else. Then basically models M1 and M2 can be formulated this way. And the difference between these 2 models is that M1 assumes that the variable Y2 does not bring any new clustering information in addition to what is already contained into Y1. So basically, then the authors propose to use a Bayes factor to compare the models, and and they approximated by BIC. So that was a different approach proposed by Fen and Shen in 2007, and they used the penalized version of the complete data log likelihood function. So actually, this approach, they showed that it works very well, but there was some criticism of this approach because they used actually very restrictive form of the covariance matrix. They actually used common diagonal covariance matrix for all Gaussian components. So, all right. Another challenge is noise and outliers. So, as you can see in this picture, even if we see components pretty clearly, there can be points that can stretch very much our components, right, and change our the structure of the mixture model even, and affect components themselves very much. So what people do here, like one of the most popular approaches, again proposed by Raftery 1993, was to actually use a uniform mixture component. So just use basically Gaussian mixture model and add one uniform mixture component that is defined over the domain of the data set. And the goal of the objective is that all these points will have higher posterior probabilities for being assigned to that uniform component. So basically that uniform component would serve as a collector of this noise and scatter. Alternatively, you can use a mixture of some heavy tail distributions, something like T distribution or contaminated normal. But basically, it's a different approach. Here, you more trying to accommodate the heavy tails into the distribution, into the mixture model. And here, you are trying to eliminate the observations that make your mixture non-normal, basically. So these are kind of different approaches.
Is your class data set always finite or could be infinite?
No, finite. Yes, finite.
How many elements should cluster contain at least? Like you can.
So it depends on the model. Like there are some constraints. Like for example, if you have a p-varied data set, right? So in order to estimate the covariance matrix, you have to have p plus 1 data points, like for example. So it really depends actually. And in mixture models, it's even trickier because you actually, like if it's a perfect separation, then this will work fine, like with p plus 1 data points. But if there is overlap, it's not as clear because some points can contribute only partially in some sense, right?
No, my question was, can one single data be a cluster?
So
So methods don't work if you have just one single.
Right. Primarily here I talk about Gaussian mixtures, and in Gaussian mixture you cannot have a cluster with one data point. But well, it all depends on how you define probability distribution. So like if you put enough constraints, you can have maybe a cluster with a couple of points. But it really depends on. It may be not very practical and it may be not very good model, but hypothetically, yes, it's possible. But again, in reality, you usually do not have situations when you are trying to model a cluster that consists of a couple of points. You're trying to like typically, but yes, it would require some very specific model with very few parameters, right? You can.
So the cluster reminds me of cover. In mathematics, you have a set is an abstract set. You have to introduce a measure or metric. So you have a metric space, and then you have a cover, and then you want to extract, refine the cover to get the covering sets to be disjoint. So there are these questions of course.
In model-based clustering framework, like it is easier to think about cluster as a sample. So if it's a sample of a distribution, can you estimate the parameters of your population based on this basically sample? If you don't have enough points, you will.
Now it makes sense. The sample is better word.
I think this is probably, at least to me personally, it's the most intuitive definition of a cluster. Because there are so many different definitions, but in model-based clustering, sort of it makes sense, I think, to think about a cluster as a sample from some subpopulation. And then our goal is to basically find, first of all, the best fitting model that would clearly define those subpopulations, right? And then we can try to make assignments based on the model we find. We can assign points to a particular subpopulation. Okay, and this is an example how influential, some observations, how influential they can be. So here, I'm not sure if you can see, observation number 1, observation number 2. And first I remove observation number 1 from this picture. You can see how it changes the clustering solution. So look, it's quite dramatic, right? So just because we remove 1 point. And influential observations are typically, like we call observations influential if the removal of this observation leads to changes in the partition, like especially considerable changes. And here I removed in the third case, here I removed point number 2, and you can see that my partition again changed quite a lot, like in red and green and even black.
Well, it's probably for you easy to see. I can't see the difference.
Oh, but look at the colors, for example. Like,
oh,
you see
okay.
here it's red,
now I see.
and now
Okay, yes.
we have only 4 points here, right? So, and same here, like green is dominating here, right? And here we have 2 elongated clusters next to each other. So this is basically just the effect of removal of 1 point. So it can be quite influential. So I have some nice picture here, but I will skip it because it's long to talk about it. Too long. Okay, now spurious solutions. This is a very serious issue that is also very often underestimated. And it is very closely related to the problem of unbounded likelihood. So there can be a situation, and let me see. Here, I think this is the easiest to see. Do you see this cluster with magenta points? That literally all the points almost on the line. So there can be a situation, and this is very practical issue actually, that your YAM algorithm will pick a component that is pretty much in the lower dimensional space. And it doesn't have to be like really in low dimension. It has to be like very close to push your likelihood very much up. And this solution will be preferred over others just because the likelihood produced will be higher than the other solutions. But the problem with this solution is that it really picks some random pattern rather than some systematic pattern in the data. So typically, what people do to avoid spurious solutions, they basically, we're looking for the best local maximizer, right, as we already discussed. But you have to check that these maximizers actually have, like, there are several approaches to check. One is to check, simplest is to check the number of points. You don't want, typically, these random pattern clusters, they have like a relatively low number of points. And mixing proportions associated with them are going to be small. Another approach is to check eigenvalues, right? Because the ratio between the smallest and the largest eigenvalues, they're going to be like very, yes.
So what's the intuition behind how the mixture model will actually end up choosing the cluster with like really poorly conditioned eigenvalues? Like I would think that it would like bias towards mixtures with covariances that look like a full dimensional set.
So you see, in this case, your cluster basically, if I draw an ellipse, right, it will be very elongated one, right? And so the ratio of these eigenvalues are going to be, if you basically it's going to be something it's closely related to unbounded likelihood, because in the unbounded likelihood, when, for example, a component is being built literally on just one observation, our likelihood goes to infinity because we have division by 0, right? Because we have determinant of sigma.
Oh, I see. So you just get a very high likelihood from that.
Exactly, yes. The problem is that you just get very high likelihood for some meaningless pattern. It's possible. And you want to get rid of this. Unfortunately, it's not very difficult to capture these situations because either mixing proportions is going to be like small. But here it's actually not very small. In this case, usually people also take a look at the ratio of eigenvalues. So you don't want like very elongated cluster. So you have to control it also. But potentially it can be an issue. Okay. We have 7 minutes, right? Thanks. All right. So now I just wanted to talk about misclassification probabilities and overlap a little bit more, because it has some very nice applications in cluster analysis. So we already talked about misclassification probability and how we can calculate it, right, based on posterior probabilities. So if we take a look at the misclassification probability omega k prime given k, we can basically, if we plug in the expressions from the E step for the posterior probabilities, we cancel denominators. This is the expression we obtain. And in case of the Gaussian mixture model, each component is just PDF, multivariate PDF. If I plug in multivariate PDFs in here, I will get this difference in quadratic forms less than some constant on the right-hand side. And basically, there is a result that I already cited. It looks like this. This is basically our distribution, and we can get this. This is the linear combination of either standard normals or 1 degree of freedom chi-squared random variables with some non-centrality parameters specified here. But anyway, despite the fact that this formula might look a little bit complicated, there is an algorithm readily available for the calculation. It's a very speedy calculation, very easy calculation. Actually, the original algorithm was provided in applied statistics. They used to, around this time, they used to publish algorithms for models like this. And basically, there was an algorithm that was implemented, and it calculates those misclassification probabilities immediately, like very fast. So what is the pairwise overlap? The pairwise overlap is defined as the sum of two misclassification probabilities, right? Because we have two components, and there are two misclassification probabilities. Our observations can come either from this component or from this component, right? So pairwise overlap is the sum of these two misclassification probabilities. Why it can be useful, like why we're talking about this? First of all, it can be useful for merging mixture components, as we discussed, because it can be used as a representative value of the overlap between two components. But there is also another very important application. Actually, we can simulate synthetic data for simulation studies and for clustering algorithms. Because oftentimes, how do people actually compare different clustering algorithms? They pick basically, as I showed you already, right? Pick some classification data set like iris or wine, run algorithm. Okay, on this data set I do better, on another data set you do better, right? And basically you find a couple of data sets where you perform better, and here we go, like we submit the paper, right? But this approach sort of allows you to simulate more systematic data sets, to produce more systematic data sets. So like you can specify the value of overlap between your components. For example, you want to have maximum overlap to be 0.1, let's say, right? And basically you control how much your components overlap. You can simulate mixtures with Gaussian components using this idea. And then you can study basically your clustering algorithms in different settings. Yes?
Yeah, so yeah, maybe just a quick question. Maybe I'm missing something, but you mentioned like the pi given y, right? It is a posterior distribution. So actually you are framing this in a Bayesian way. You are assigning a maybe directionally prior to the pi's, and so that you can compute the posterior. Is that right?
So here it's so basically this is the Bayes rule, right? This is the Bayesian decision rule. So we compare basically posterior probabilities.
Yes. So the prior, so there are priors for the like the
PR is the probability. You mean PR?
No,
probability.
the tau.
Tau is the posterior, right? Posterior probability.
Oh, okay. Oh, okay.
Tau is a posterior probability. I just put dot because in the past we had tau ik probability that observation xi belongs to the cave component, right? But because it's not related to a particular observation, right? I just put dot instead of I. Okay, so and basically this idea got implemented in Mixim in R, and there is also a version for MATLAB written by Italian folks and implemented in their FSDA library. This is a group from European Commission who apparently uses this idea a lot. And you can control actually in the package, you can control both maximum overlap and average overlap. It's maximum pairwise and average pairwise overlap, and you can control both of them at the same time. So sort of to give you more flexibility. But again, I think this is a good idea in the sense that you can produce much more meaningful clustering data sets, and you can consider different settings where you have more overlap, less overlap, more complicated situation, less complicated situation, different number of components, different number of variables. Like you can control many things, like same covariance matrices, spherical, etc. Like it's very easy basically to set it up. Overlap, right, defined as the sum of two misclassification probabilities, and we talked that, about potential use of overlap for simulating data sets with pre-specified level of clustering complexity, right? So now I will talk briefly about the overlap for what is called transformation mixture model. So as you could notice, up to this point, we talked about Gaussian mixture models. They are really good for modeling like elliptical clusters, right? But what happens if we have something with skewness? And it would be nice to be able somehow to simulate also data with skewed clusters and be able to control the overlap. This is basically the idea. And this is what we can actually do. There are some papers on what is called transformation mixture model. The idea is the following. Imagine that you have the data set. We will actually talk about this a little bit in more detail later, but the idea is the following. Imagine that we have the data set with skewed data groups. And or maybe even think about just one data group. We have data group that is skewed, and we would like to apply some transformation. And there is an abundance of transformations. Like most famous probably is Box-Cox transformation. It's actually probably one of the worst that you can pick, but but it's the simplest and it's very popular also. It's like K-means in transformations probably. Okay, so but if you have some transformation, and there is mainly transformation and really good transformation proposed by Gillen Johnson, and I think it's 2000, but maybe I'm wrong. The idea is the following. Imagine that you have some function that transforms your data into normality. Like it can be univariate normality, potentially multivariate normality. Again, I'm just giving a sketch here. And the transform data roughly follows normal distribution. Then, if we apply back transform, we can basically write down the PDF of the original data set. It's like very simple transformation problem, right? So here it's going to be normal PDF, p-variate normal PDF, applied to the transform data. Actually, mu k and sigma k are the mean vector and covariance metrics for the transformed variables, and this is just the Jacobian related to the. Okay, this is Jacobian related to transformation. If we use this structure for the PDF in place of the components, we can get the following mixture model, right? And this mixture model actually can take into account skewness. And this is what we can do for the overlap. So here we will assume that the parameter lambda is transformation parameter, or you can think of it as a skewness parameter also, because it serves actually the skewness parameter in our setting. You can see that I take it without subscript k, so it's going to be common for all components. It's going to be exactly the same transformation parameters. It's needed for what happens afterwards. So you can see that I can write exactly the same expression for the mixing proportion, right? My y now follows this distribution, this transformation distribution. Now I plug in literally the formula for the posterior probability. Denominator cancels. This is numerator for tau k. This is for tau k prime. And you can see that basically the Jacobian part goes away, right? Because we have the same lambda, so it basically cancels, and we get to the expression where we have actually our original expression for the overlap in terms of the Gaussian, multivariate Gaussian density functions. This expression is literally no different from what we had before for Gaussian components. It's the same. And what do we plan to do with it? Actually, we plan to do, this is our plan of attack basically. We plan to simulate Gaussian mixture model. And then for the Gaussian mixture model, we are going to find some skewness parameter lambda that skews our clusters more or less according to some pre-specified level of skewness. We will talk about this in a bit. And basically the overlap, when we transform all the components simultaneously, the overlap happens to be exactly the same. It does not change. So basically this way we can actually simulate skewed clusters with pre-specified level of overlap very easily using same package mixin. Okay, there are multiple definitions of how we can actually specify the multivariate skewness, but we actually adopted the proposal given by Mardia in 1970. This is the formula, and basically you can design the following algorithm. This is pretty much what I just told you. So we simulate the initial Gaussian mixture model, and then we find for the pre-specified level of skewness, we transform the data accordingly so that we control either maximum skewness or average skewness observed in our components. And we can then simulate observations from our transformation from our transformation mixture model. It's very easy. We simulate the data from normal, and then we back transform basically, and we get with pre-specified levels of skewness, and we obtain the skewed data groups with exactly the same overlap as in the original Gaussian component. Gaussian mixture model we simulated our original data from. Does this make sense, more or less? So this is helpful because we can actually get clusters. These are like some density plots. You can see that skewness is equal to 0. This is like Gaussian components. And then this is just little skewness. You can see that some clusters get some skewness. This is average skewness over all components. And you can get them more and more skewed according to this algorithm. But basically the overlap is preserved at the same level. So this is really convenient. There is some related idea also for the cluster-weighted models. So cluster-weighted models are very closely related to regression mixture models. Regression mixture model is just a mixture where you basically have a response y, and you are supposed to have like fixed explanatory variables. So these x's are considered to be fixed. So this is like a conditional basically distribution. And what is interesting about this, that basically the mean function of course changes, right? So the mean function is x transpose beta k, so your mean changes. It's not fixed mean anymore. And there is, now let's talk about cluster-weighted model. Cluster-weighted model is actually very popular nowadays. Like many people like using it, and there are multiple papers right now on cluster-weighted model. But essentially, this is nothing more than a very simple extension. So here we assume that x is fixed, and in cluster-weighted model, we basically assume that x also follows some distribution, and then you can see this is basically marginal distribution of x, and this is a conditional of y given x, right? So basically, you model y and x jointly this way. And that group in Italy that I already talked about, they tried to somehow, for what they do, they had to simulate data from cluster-weighted models with some pre-specified overlap. But the problem is that if you think about several regression lines, right, at different points x, your overlap is going to be different, right? And it's not very clear how to calculate these misclassification probabilities and how to calculate these overlaps. So what actually what they did, and they published a paper on this, they calculated the overlap for the means, basically, for the means of two clusters. But this is what you can also do. So based on our definition, this is again based on our definition pretty much, we can formulate the probability of misclassification, right? This is exactly the same as what we had before. It just we put the different components in here, right? And first we define the probability of misclassification as a function of x. The reason why we want to do it is just because it will be much easier to first to consider it for the fixed x, right? And you see we will basically take an integral here where this part in the middle is going to be exactly the overlap as a function of x, this part inside of it. So basically I do, to calculate this misclassification probability, I use condition here, so nothing overly complicated. And then as a result, it happens that actually misclassification probability omega k prime given k is nothing else as the expected value of this function of x. So, and this is of course very nice because we can very easily calculate this value, this expectation based on the distribution of x. So in some cases it basically takes the form of chi-square distribution with 1 degree of freedom and non-centrality parameter delta squared. And this is for omega k prime given k, okay? But we need the distribution of x I actually have not specified. So distribution of x can be anything. And, but it's not a big problem because we can just use the convergence in probability very easily to estimate the misclassification. So basically we simulate a bunch of points from x based on the distribution, and then for each x we calculate this misclassification probability for x for different x's, and we can calculate the overall misclassification probability. And again, overlap can be used, like we can define it in the same way. So this is how basically it looks like, that you can calculate the overlap between different clusters. And this is like small overlap, 0.05. Here we increase it, and here you can see it's already considerable, like 0.4, very substantial overlap. So this is also actually a very easy way to calculate the overlap for cluster-weighted models if there is a need for that. But again, like despite the fact that cluster-weighted models are popular nowadays, I think still that Gaussian mixtures are still like by far more popular, and it's probably the first part we talked about is much more useful. It's like a partial case basically. For some situations with cluster-weighted models, yes, you can sort of calculate the overlap also in a nice way. Okay, so that was, I think, pretty much what I wanted to talk about, to tell you about the overlap. Now, I will briefly talk about some parsimonious models. And what's the idea? So there is a package, mclust. That's probably some of you heard of mclust. It's a very popular package, the most popular, by far the most popular package for Gaussian mixture model. And it implements 14 different parsimonious models based on eigenvalue decomposition. So the idea is the following. You can, by changing the eigenvalue matrix or eigenvector matrices, putting constraints, like for example, they are common for all components, or diagonals, or this eigenvalue matrix is common for all components, or other constraints, you can actually control the shape of clusters you obtain. You remember yesterday I showed you an example in the my very first example, I think, was contours for the spherical Gaussian component with equal covariance matrices. Actually, it can be very easily constructed using these parsimonious models. So basically, there are 14 different Gaussian mixture models that you can incorporate very easily in mclust, that you can basically run. If you want, let's say, elliptical clusters of the same orientation with different volume, you just choose a particular model, you specify it, and you have it. So it's very nice idea. And why is it actually a good idea? Because we want to reduce the number of parameters. If you think about how many parameters are associated with covariance matrices, right? It's a quadratic function of dimension. So we don't want to have that many parameters oftentimes because we're under the risk of overparameterization. Okay, so some common component choices. We already talked about transformation mixture models. I talked about Gaussian mixture models. If we want to model heavy tails, some typical choices are T for contaminated normal. For modeling skewness, it's either transformation, skew normal, or there is a package for generalized hyperbolic distributions. If there is a need for modeling heavy tails and skewness simultaneously, we can use UT distributions or contaminated transformation distributions. Okay, now we will talk about something else. So basically, we already talked about regression mixture model. I just introduced what it is, and oftentimes we choose basically Gaussian component for modeling regression. And cluster-weighted model, we just talked about it as well, right? So this is a cluster-weighted model. And again, the common choice, very often we choose like Gaussian probability density functions for the marginal distribution of X and for the conditional. But now let's take a look at the following idea. What if we take a look at the cluster-weighted model? The idea is the following, right? We have Y conditioned on X and the distribution of X. What if we consider more conditionings? So this model is actually called conditional mixture model. The idea is the following. Let's rewrite our joint component distribution as just marginal and the product of a bunch of conditionals, right? So we can actually do it. What's the advantage of this? The advantage is that we can get actually a form like this. X tilde here represents the vector that starts with 1, and we have all X elements up to the element xj minus 1. So basically, so that we write the condition here. this zeta represents the parameter vector. So then, if we rewrite our joint component distribution in such way, we will basically have a product of many distributions, actually of p distributions, right? What's the benefit of that? Actually, the benefit is that when we take a look at the Q function associated with this, we will have a bunch of regressions, very simple models with parameters that are very easy to estimate, right? Basically, we do not have to deal with those complicated forms of covariance matrices, right? We do not need to deal with covariance matrices like with different volumes, different orientations, etc. Because everywhere for each regression we are going to just have just one variance parameter. Where is the catch? The catch is that we will have a whole bunch of linear regression coefficients, right? Many more regression coefficients here. But we're maybe going to deal with this. In the partial case, when dimensionality is 2, if p is equal to 2, this model is basically essentially exactly the same as a cluster-weighted model. So, and here is the EM algorithm. So everything is as before. This is our E step, M steps. We can get beta coefficients very easily, and the variance can be, so everything is in analytical form. All expressions closed form. This is nice. But what if we compare this model with the original Gaussian mixture model with unrestricted covariance matrices? We have k minus 1 mixing proportions. We have k times p mean parameters, right? Parameters associated with k means. And we have it has to be divided by 2, okay? Divided by 2 here is missing. Dispersion parameters, right? So unique parameters associated with covariance matrices. But in the conditional mixture model, we have exactly the same story. So the number of parameters is exactly the same, also missing over 2. So, okay, seems like we have no benefit in terms of the number of parameters, right? But the advantage of this model is that literally we have several regressions. And for regressions, we can very, very easily eliminate those slopes that are not needed, right? There are like well-established regression techniques, and we can apply them immediately to get rid of those slopes and for some components that we don't need, right? So what's the benefit actually of that? We can drop the number of parameters almost always tremendously, very easily. Algorithm is very fast, right? And in addition to that, each component, we can drop unnecessary slopes for each component individually. It's not that like in M-cluster, we're trying to, let's say, provide the general form of clusters. Let's say all clusters have the same orientation. No, here we can be very specific, right? We can, I don't know, choose 2 components for the first component, 2 slopes for the first component, drop all slopes for the second component, and have 7 slopes for the third component. It all depends on the particular shape of component. So this is a big advantage because we can literally model each cluster individually. Make sense? All right. But this is actually not the only advantage. If we think about what we can do with our explanatory variables, it's very easy to go to something like higher order, high degree polynomials, right? We can actually model curvatures, right? If we take a look at not just x, but if we include, let's say, x squared for our explanatory variables, we can start moving, we can start modeling clusters that look like have quadratic shapes. And we can continue that process. Actually, in reality, like in what we tried, typically this quadratic curvature is sufficient. But it happens very often in data that we have some curvature in clusters. It's not like perfectly elliptical. So that's a very useful idea because we can considerably extend the class of models we obtain. And the EM algorithm does not change, right? Because it's just explanatory variables. So the estimation is going to be pretty much exactly the same. Yes, we're going to have a little bit more slopes, but if you want, you can introduce interaction terms, etc. Right? So this idea is actually very simple to implement. Okay, now it cannot be all that good, right? There should be some issues. Yes.
Is there a known connection between the polynomial degree and a certain class of transformations? You were talking about those earlier about transforming your space. Is there a known connection between?
I don't think there is.
This kind of induces a transformation, right?
Like I don't think I think about it as a transformation.
Okay. I don't know. It sounds like it produces clusters that are no longer Gaussian.
But it actually, well, the thing is basically.
But each component.
What we are getting this way, we are getting that we're not transforming actually our data, right? But what we are getting is that we can actually model clusters like this, with some curvature. So one cluster can be like this, another cluster can be like this, and a third cluster can be like this, for example. But it's not that I like.
But you could also capture those by transforming your domain.
Well, with some function, probably, yeah.
Yeah, but that function's not. There's not a known relationship.
Yeah, yes. So to be brief, yes. Yep. Okay, so back to shortcomings. One clear disadvantage of this approach is that order of conditioning, of course, will change everything, right? So how do I know what is the optimal order of conditioning? And here is a very small example. So here I have a marginal, right, distribution of x1. Here I condition x2 on x1 and then x3 on x1, x2. And here the order is different, and of course the model is going to be different. So, and if we have many variables, well, we have a whole bunch of different ways how we can actually do this conditioning. We can try to do all permutations, but like it's not practical in many situations, right? So as a result, we propose to use a different approach. So this is what we can do. So we first start with generating P proposal models. Here we take a look at the joint. Basically, we start with the joint distribution for all P Gaussian, for all P variables. And now we're trying to separate just one variable at a time. So this is like marginal for one variable, and we condition all the other variables based on like on x1, and here on x2, and here on x3. And we basically we're trying to separate one variable at a time, take it out from the joint. Let's say the first model is the best in terms of like based on DSC, right? So we can. Let's assume that the first one is the best. What do we do next? Next, we propose another P-1 models. Here we do x2 given x1, and x3, x4 up to xp given x1, x2. And here we again try other models. And we keep this process, we keep doing this process until basically we decompose the entire joint distribution. So this is what can we do. Surprisingly, it actually shows very, very good performance. Of course, finding the best model is not guaranteed this way, but it's like much more practical. Like there are some examples. If we have P is equal to 5 and we go for all possible reorderings, we can get 120 models. For 10, we have more than 3.5 million models. So of course, at the same time, this proposed algorithm has 14 and 54 just as a comparison. Okay, here I had some simulation. Maybe I will just very, very briefly go over this. We wanted to take a look at whether this approach even works, right? And as a comparison, we have chosen other packages HD Classif, Mix GGM, mixture of Gaussian graphical models, MClust, of course, because it's the most famous, and our package is basically CMBClust. Of course, we simulate the data from our model, right, and we even have like some curvature, so we totally expect that we're going to do better, but at least we want to see that we're doing better, because if we're sort of simulate from our model and we're not even doing better, then it's a real concern. And you can see this is like average BAC values and adjusted rand index, and we actually simulated from a 3-component mixture model. Because of this curvature, all other methods cannot actually take it into account, right? Because they sort of try to do like something related to Gaussian mixture models. And if you have this kind of curvature, right, what really happens, you basically, other methods will do something like this, so they always overestimate the number of components because they're not able to model the curvature. So, so basically this is what we expect. In all cases we do considerably better, so much better. And this is also the case here. And in this situation, this is the IRIS dataset. So we run this. Oh, by the way, in all these cases, except for the IRIS, and next slide I will show the results for all permutations possible. In all these cases, we used our algorithm where we basically choose the order of conditioning based on this decomposition idea. And so basically what I wanted to show you that our BAC is the best here, adjusted rand index is not the best, actually HD Classif does similarly. If we go to another data set, oh, this is IRIS actually, but now we consider all possible orders of conditioning, right? So 1, 2, 3, 4, 1, 2, 4, 3, 1, 2, 2, 4, etc. What I wanted to show you is that actually, if we take a look at k equals 2 and k equals 3, for L equals 1 and L equals 2, look, MClust produces with parsimonious models, produces BAC 561, right, BAC. And actually, all these values, no matter what kind of conditioning we use here and here, all these values are actually better than MClust. Even our worst solution is worse than MClust solution, basically. So it's actually very promising. So for crabs, we also were able to detect the correct number of clusters for, but actually in this case, it's a fair comparison. You see, if we don't do the best, I still show you. So HD Classif was the best performer, but we were second. For fish catch data set, actually it's a difficult data set. We still identified the presumably correct number of components, because strictly speaking in these classification data sets, nobody knows what's the right number of components. Right? People assume, because they have a categorical variable, that that categorical variable is basically what you are supposed to find, but there is always no guarantee, right? And you can see that BAC is by far the smallest, and adjusted rand index. This is actually a good example of why it's so important to find a good model. Look at difference in, this is what I have in bold here, this is the best result produced by a particular method. And look, adjusted rand index is 0.35, 0.496, 0.843, and we have 0.896 because our fit is so much better. So this is very crucial to provide to find a good model and good fit. And I think one more data set, it's kidney disease data set. So it's also, we basically have people assume that there are 2 clusters here, but we found 3. Just model fits better for 3 clusters, and still BAC is the best, and adjusted rand is the best. But if we had 2, it would be even better. It would be like very close to 1 actually. And final one I think is 1. Also we do very well. So basically summary for this model is that this model seems to be very competitive, and it's a very recent actually approach. Like literally we wrote the package for this last year. So this this approach can be used for modeling non-compact clusters. We can use this approach, like it's really fast, despite the fact that we need to do this variable selection for regressions, and we have a bunch of regressions, but calculations are so trivial, everything is in closed form, so it's actually really fast. And we can, what is very important, I already emphasized that we can actually model each cluster individually. It's not that we assume some common family, like all clusters are quadratic, right? All clusters are elliptical with the same orientation. We do not impose any constraints on common constraints on clusters. Each cluster can be very different from others. Okay. All right, and here is a brief summary of popular mixture modeling software. So, if you are interested, MCLUST is, as I said, for multivariate normals. Mix SMSM, this is multivariate skew normal. Model plus hierarchical model clustering. MapTransMix, this is transformation mixture modeling for multivariate and matrix data. ClickClust, I will talk about this in the last day. This is clustering categorical sequences. MixGHD, I mentioned that it's a mixture of generalized hyperbolic distributions by Cristina Tortora. This CMBClust, this is the package we just talked about. And there is actually 3 packages currently for mixture simulation. I would recommend mixing. But like it's your choice. Other methods, actually, the other packages, they rely on some projection, basically, and some separation indices in lower dimensional space, basically. But of course, you can do some information. So, all right. So we have like 15 minutes, and like I would like to at least to start and talk about this problem. I really like it. And it might be of interest to you. I thought I would show it as an illustration for how we can actually apply mixture models in some somewhat creative way. So this is a data set available from USI machine learning repository. It's recognition of handwritten digits. Okay, and there are 44 writers apparently who are asked to write 250 digits. And they used the tablet and the stylus for that purpose. So what they did is the following. So they had basically a tablet, and they were drawing, let's say, 0 with the stylus. And what they have done, they basically recorded 8 data points along the trajectory of the stylus. So 1, 2, 3, 4, 5, 6, 7, maybe 8. Okay? So they recorded the trajectory. So, and they have X, they have Y, so basically it's a 16 dimension, it has 16 variables, 16 variables data set. So, as I said, each image is summarized as 8 pairs of coordinates along the trajectory of the stylus. That's a processed data, so there is some scaling and shifting applied. Data has been split into testing and training data sets, and testing is known from literature to be considerably more complicated, and we will consider testing data set for this purpose. So this is an illustration of what you actually observe, these digits. Like here, for simplicity, we focus only on 0s, 8s, and 9s. And the question is, like, visually, they're quite easily, like, recognizable, right, these digits, like, more or less. But how easy are they to cluster? So if we do Gaussian mixture modeling, we can actually see that our adjusted rand index is so far away from being close to 1, right? It's 0.295. And this is true IDs because we know which ones are 0s, which ones are 8s and 9s. And this is like estimated classification. We can see how many misclassifications we have around, primarily because of the 8, right? But there are some other issues also. But why is this data set so difficult to cluster? Do we have some skewness or outliers? Maybe 16, it doesn't sound like very high dimensionality, but maybe it's a reason. Or is there any other issue? So, in order to figure it out, we actually redraw these pictures just in a little bit, so with arrows provided. And you can actually see that we have different writing styles for these digits, right? We have zeros, eights, and nines written in different way. So, for example, some zeros start somewhere in the left top corner, roughly, right? And some zeros, like, I don't know which one, like this one, right? Starts here. Take a look at eights. This eight starts in the left top corner. This eight starts in the right top corner, right? And although visually we do not see much of the difference, right? Basically, we can see still that this is 8. If you think about the data points, right, they are going to be very far away in the space because of how the digit is drawn. So, but one possibility, it's just an idea that we will build on. Maybe we can change the order of the coordinates in such a way that we can actually get digits closer to each other in the space. So we can say there is some standard style, like style 1, and this is basically second digits. If we change the order, maybe we can get a picture a little bit more similar to the first style, right? Like this 0 can be made more similar to the first one. And similarly with 8s, so we can see that we can try to make these digits more similar to each other. And with 9s, and 9s are very complicated. Actually, 8s are also complicated, because if you think about how people can draw 8, I think there is a whole bunch of ways to write 8. Even myself, sometimes I draw 8 like this, and sometimes I do like this. And I have no pattern, I believe. I don't know why I do this. And some people can do it this way, some people can do it in the opposite way, right? But for now, for simplicity, we just consider the case with, it's basically, we consider a subset, and there are some, like, there are writers of these digits that write these digits in a very particular way, because we had overall, we had 44 digit writers, right? But we will generalize it in the end.
Can you say again what the task was?
Task is to cluster the data set, basically. Potentially for semi-supervised clustering, when you have some data labeled maybe, and some bunch of data sets, the data points are unlabeled, and you want to produce clusters, basically.
Yeah, but what you're saying that it is challenging in what sense? Like so if you have different writing styles, do you want to take it to the clusters by writing styles or clusters by data indices?
So in the end, I want to know whether it's 0, 8, or 9. But yes, it's a good point, because like, and this is what we're going to do. We're going to also detect the writing style, actually. Yes. Yes.
So when you evaluate the clustering algorithm on a classification task, I saw that you made like the 3x3 chart of the true labels and the cluster labels. Like, do you have a systematic way that you assign like the 3 different clusters to 0, 8, or 9, or do you just like say, okay, this is like the reasonable thing to assign to 0 and whatnot?
No. Like for these digits, it is known which digit it is. So I know the true classification.
Oh, so in that table, both axes were
exactly. So on the rows represented true classification, and columns represented estimated classification just based on Gaussian mixture.
Oh, okay, I see.
So I am just comparing how well estimated classification matches the reality, basically. And it wasn't. But we will try to sort of improve it. And so this is the story with 9 also, right? There are different styles. You can see that some people draw 9 this way. This is, I'm talking only about those specific writers. And some people draw 9 in this way, right? And also, by changing the coordinates, we can at least make them more similar. Okay, and this problem actually, not specifically this problem, but related problems are known in literature. They are known as measurement inconsistency, and they can be generally divided into several classes, like transposition error. These are like very often happen. These happen very often in clinical fields, where a human operator basically records the data and just some variables got swapped. Just maybe x1 is written instead of x2 is written instead of x1, and it just happens. Conversion error, where data use different units, like miles versus kilometers, right? Pounds, kilograms, and things like that. Then interpretation error. Sometimes if you have a survey, right? 1 to 5, some people can think that 1 is the highest rank, and some people can say that 5 is the highest. So this is interpretation error. Or there are sometimes just different various recording styles, like in the example that we consider. So the idea, I'll try to do as much as possible in 5 minutes, okay? Maybe we'll continue just a little bit tomorrow on this problem, okay? So the idea is to, here we introduce basically, this one is closely also related to the transformation idea. So x1 will represent the standard style, x2 will represent an alternative style. For now, we just consider 2 for simplicity. And we assume that the alternative form can be basically turned into the standard form using some known transformation. Known transformation because I can observe actually the way how people write it, right? These digits, and I can figure out what the matrices A and B are, basically, and just rearrange the elements. And then x1 will be normal mu sigma, then we can get normal distribution for x2, basically in the following way. And now if we assume that we have k classes or k components, we can actually, and we assume that each component has, so in our case, these are going to be digits, and each component has mk representations, alternative. So one is basic standard representation and mk minus 1 alternative representations. We can actually formulate, we can write down the following mixture model here. So we will refer to it as measurement and consistency Gaussian mixture model. Okay, so here we have one more unknown variable, because zi, this is the same as before, this is an unknown group membership label, but here we will also have unknown representation label, because we don't know for each digit which representation it follows. So then we can write down the complete likelihood function this way, and we can get the EM algorithm also in a very nice way, quite simply. And let's take a look at what happens here. We can actually, you can see that just by examining our digits and applying these transformations, we can increase our adjusted rand index quite considerably. Well, you can see that I have 2 styles for zeros, 2 styles for 8, and 2 styles for 9. What's the basically disadvantage of this approach? I need to examine these data sets, right, and identify these styles. Even though, we will build on this still, we will improve it further, but I think even this one is actually like a reasonable improvement, because identifying these styles, in how many ways do you think people draw 9s? Yes, maybe 20 different ways, but sort of it's like possible to actually, if you think about how many parameters we need for each additional representation, it's actually just one mixing proportion. It doesn't require anything pretty much. We just need to identify this set of possible reorderings of the coordinates. So you can see that basically we improved it very much, right? If we take a look, okay, 2 minutes, fantastic, thank you. So this is basically an illustration of where our methods are going to work and where our we fail actually. This is the solution obtained by Gaussian mixture model. This is the solution obtained by our mixture model. If you see this red shade around the digit, it means that it was misclassified. Okay, so then these are zeros. These are just sample zeros. These are sample 8s. These are sample 9s. Same zeros, same actual digits here. So, okay, for our method, you can see that this 0 was not classified correctly. Why? Look where this 0 starts. We didn't take care of this representation, basically, so expectedly it can be classified in the wrong space. Look at this. This is supposed to be 9. I think we're not even expecting to classify this, but it's 9. So, so it makes sense. And this is, if you take a look at the mean profiles, this is basically true based on the true classification. These are digits. If we take a look at the classes obtained by Gaussian mixture model, and these are basically our digits that we obtain if we average. These are standard basically representations for these digits. And I think, okay, so as you can see, we continue with building on this a little bit. I think if it's okay, probably we'll spend like 5 or 10 minutes tomorrow to finish this. Okay? All right. Thank you very much.